lot of things to do. And okay, let's start with a new energy. So there's a couple of questions, I think, from like a couple of students about the class. So let me ensure you like whatever I talk here, I think okay, the topic that I dig into, like I give you some reference, or like the Professor Tan just updated, and the BKEL with quite a few reference, and then also like some PDF file. I encourage you to go and read those things. Encourage, right? But it's not required, because I know that, again, I just emphasize that it's not like your main class. This one is really a very interesting class, but you can like just get into that, read whatever you can, and then the requirement will be like because okay, let me like have some clarify something for you. This class actually is the summary of about 6 or 7 books, so it's no way that we can go through that in detail. So you can see that if I give you the reference, if you go in there, it will be a lot of things. And even like because of it, what I expect from you is like I got some ideas of the concept, and also like the thing with my like the question I will give you at the end of this chapter. If each chapter, if you can answer that, it's good. You don't need to be, the thing you learn a lot is from the lab. That's like from for the practice. But the things learned from here is like you will have a general concept, things what happened, where we are, and so on. And then you learn quite a few things about like, oh, what do we do like somewhere like in the world, what people doing, and then where's the state of the art, something like that. In the middle of like my class, I will talk about that so that you guys know like, okay, there's here's people doing that and the ways doing that, and so on. That's like the thing I expect you to know, but it won't be like so don't worry that like there's something like very in detail, like you don't understand. If you don't understand something, just ask. But I think the key thing is when I give a question at the end, it's supposed to be like that's supposed to be the question like you need to understand. If you don't, you need to ask, because it's supposed to be like in the, that's my expectation, right? So my expectation is not that much. So you can see like what, and then you just like go, and then like and for like also is but one thing I think about as I talked before, the main thing that you guys need to learn is about the skill to write the Verilog coding. So that's the main thing. I encourage you to be skillful, to master that skill, because that is very useful for like when you apply for the like for the company that need you to work in this industry, in this field. If you know how to write like a Verilog, that's a plus, a good plus. So because of it, I think in the PDF file I sent to Professor Tan, and then like uploaded to the website, like the BKE website. There's also like the slides about the Verilog HDL, and also there's also a link to a book, a very good book about the Verilog HDL for the synthesis. So that's really, I encourage you to do that. This chapter. So okay, so that's the first thing. Like the main thing I want to like want you to know is, don't worry about like the detail. You need to get some idea, you need to know, but it's not like go to very much in the detail. All right, so with that, I think let's start. By the way, I think if you have any question for the first 2 chapter, right? For the first 2 chapters, you can ask along the way. or like going forward, whatever in the past you can ask to. Don't worry that okay, this one is from like the first or the second chapter. Just ask, because the longer you wait, the worse consequence it will get, right? That's like always the case in every cases. All right, so let me share for the chapter 3. What is it? Okay, here it is. Okay. Okay, this one is the one I think. Yeah. Okay. This chapter, I think we will go through this chapter for about 4 or 5 weeks. So I think the focus will be on the. You can see that there's a logic design, there's a RTL design and verification, logic synthesis, and again verification. So there's a 3 main focus here. First is the RTL design and logic synthesis and verification. This one, so this one RTL design means like you need to like retool your skill on VHDL, and then you need to learn how to do logic synthesis. This one will be like in the lab, because here we don't have the tool, we don't have a software to like specify what we need to do. So I encourage you like during the lab, try when you do that. For this one, for the logic synthesis, this is what you will do the lab, and then during the lab, I encourage you to do like vary the recipe, which is a very the script. When you run logic synthesis, there will be the recipe script. So you run that through, you get the result, right? However, you run that, it's easy because you just like read in and then write whatever like in the lab described to you, then you write the result. That's the first thing. That's the first step. During the time, try to have try to understand and modify the script to see that if I do this, what is the outcome, right? So usually I think in the lab you can run only one, but if you can run that 2 or 3 or 4 or 5, whatever is allowed, run a couple of things to see like when you do that like this way, what is the outcome? When you do this way, it's the outcome. Like that, you learn how logic synthesis work, or like you learn. Because if you just like enter, like I remember when we do the lab, usually there's a example. You just enter it, you run through, it pass, then you get it done, and it's done. There's no use to do it, because what if you do that way? You just a push button person. A monkey can do that, right? A monkey can like do that because they just push button. As here we call that like the monkey task. So if you do that, it's not engineer. Engineer is you have to question, why do we have to do this? And you question, then you got the answer. You can ask your like instructor at the lab, and then you can ask them why. And then if like they busy, so you can try to answer yourself by varying that, by like adjusting, modifying your script, and try to see. Only when you debug, only when you make a mistake, only when you make like a bug, that you learn how it works. Because you know that, oh, I made that this one, I do that, it didn't work. I know that, okay, this one didn't work. But if everything get through, then you have nothing to learn, right? It is like that. So again, I think go back to this. I think this step during the lab, try to use your time at the lab to do that, because you have the tool to do the logic synthesis. So try to maximize your usage of the tool, of the software. That's your knowledge. That's your skill. The other one is RTL design. The same thing. RTL design, when you write something, the thing is you have the software. So it's kind of like the difference between like learn with practice, and it's different from like the theory learning is that when you learn with like I think if you know we said that like học chay, right? Which means like you just learn the theory. There's no practice. That's how like it doesn't work, because you write it theoretically, it looks like okay, but when you apply it in the practice, there's a tons of things like happen, and then there's a lot of like fine thing that you don't know. And if you, I guess you know the some kind of saying, right? The devil is in the detail. So what you learn about theory is one thing, but when you apply and you write it, that's another thing. Nothing is comparable to practice. No matter you are so good at theory or not, you still need to practice, because by practicing, that's how you you understand the thing and then like make it your own. By practice, you make your knowledge, not knowledge. You make your class to be your own thing. If not, you don't practice, you won't remember anything. After the class, you will return everything to, they say that like trả hết cho thầy, right? So if you don't practice. So again, I think the another one is a logic design. This portion will be like the portion I think we talk about the quite in the like a digital design. So I think okay, with that, I think we have a three portion, which main thing is a ITL design. The verification too. Verification is related in this case related to the simulation. Simulation, you have a tool for simulation, so try to use it. Okay, the key thing, okay, bottom line here. So the main thing I want to say here is no matter what you do, when you get into the lab, you have occasion, you have the opportunity, try to use it. Your opportunity here is you have a chance to verify what you think. Because sometimes you ask the thing, you ask me, I answer, or like somebody like the people like with ask, you ask, they think one looks like it's good, but when you apply, you put in the tool, it didn't work. The reason is not that it's not because I'm wrong or not. It's just because the tool might behave differently from tool to tool. So the question when you ask the teacher, it can be like his answer might be good, but it might be good for this tool, but not with the other tool. The same word, the same terminology might mean differently from one tool to the other tool, which means like whatever you think, you have to apply to the tool to see like what happened in this case. Remember that anything like there's no like absolute truth in this. You have to learn, and then like you have the bottom line is that you need to practice. So the lab is very important to you. I encourage you to don't waste any time in the lab. Don't skip any lab. That's what I meant too. Don't skip, because that's really like the very good, like a valuable time for you to learn this thing. Everything I talk here is just like it's like a summary. You learn concept, etc. But if you don't take the lab seriously, I think nothing will be left with you. All right. So three things: ITL design, verification, and logic synthesis. That's the three main focus of this chapter. This one is just a review, right? So I said where we are in the flow. So this one is where we are. That's like the you can see that this one LSI design is, this one is like we'll have a synthesis and we'll have the layout design, but I think the one we focus even like a narrower than that in this chapter, which is only logic design. So this one again, where is it? This one. So this chapter is just focused on the logic design, which is like the first step in the whole flow of design. The second step there's a two main steps of the design. The first one is logic design, and the second is here's called layout design. I think usually people go on that physical design. And then we have a test design. This one is a portion, is a part of the physical design. This one, test design, it means like design for test, DFT. Okay, this portion is the one we will focus in the chapter 3. Right, you have a system design, define the spec, define the structure, the architecture, and so on. Then you have a logic design, test design. Okay, all right. I think you guys can this one is that you can note it as like a DFT. This one as a physical design, PD. Well, now with this logic design, that's what I'm talking about, right? So in this, you can see that it is composed of 3 main components. First is logic synthesis from RTL to gate. RTL is a register transfer level, which is like it will describe the design as the logic between the flop. The logic between the flop, it can be defined at different level, like a behavioral level, or like the structural level, or like a data flow level. We'll go into detail later. But at the end of the logic synthesis, the output would be a netlist, which is a file. In that, it will include, it will describe the cell it used, which is like the NAND, NOR, multiplexer, SOR, whatever, every like cells provided by the library, provided by this one. Yeah, you see, sub library, cell library. So at the end of the synthesis, it will describe the design by using like the cell from here. And then if define that not only like it has the okay, put it this way, like to be simple, it's like the Verilog HDL, but at the structure level, which is you have it will like show you the cells are used and also how those cells are connected. So at the end of that, it's only that there's no more like the behavioral description is only structural description. And then the second is a logic verification, and you have the timing verification. I think in here there's a portion in here for like writing the RTL Verilog HDL code. That's the one I think is embedded in the logic synthesis. Now there's also the rough PNR. PNR here is a place and route. So placement and routing. Rough means like rough, right? It's kind of like simple. The reason I think, as I talked like previously, when we do the synthesis, when this one is like this information will be fed into the logic synthesis. The reason is, I think, for example, when you have the cell, let's say like a simple circuit, right? A simple design has only 2 cells. Only 2 cells. Okay. Here. All right. Come on. Okay. Two cells like that. If I have these 2 cells, so because I have only 2 cells, then I can put these 2 cells next to each other, right? The distance here maybe like 1 micron. And then you have a 2 like that, 2 input, this one like this, and this one like, for example, I like go to, for example, this simple. So because of it, this one is a Y, right? This one is a Y. So Y delay, and this is cell delay. So because it's simple, in this case, the Y delay is a 0, almost a 0. So you don't have to worry about that. But when you have like let's say not much, it's about 10K cell. Then even that, this one, like this cell, right, cannot be placed like next to this because of the constraint. So it will be like you go like somewhere here. Because this place is taken by somewhere else, you go to somewhere here, right? Now the Y now go further. So how can the synthesis knows it? Know it? It cannot know. So it only knows if we feed it some information. So because with it like so that means that the first synthesis there will be no PNR information. But when we take the netlist, we do a rough, right? Like kind of flush the flow. We run the first synthesis without any PNR. We take that, we go to the PNR flow, which is the physical design. We place it, route it. Then after that, you have a roughly some idea where the cells are placed. Then we fit that back. Now the tool can know that, okay, now after that you fit it back, the tool can know that, okay, this cell and this cell is far away. So it can like now read and then it model like the Y like that far instead of like knowing this, right? So in the old days, they don't have that choice. They just like they don't have the choice like they feed back the information from PNR back to the synthesis. So all they can use is the Y load model. I think you said there is a Y load model. Y load model. This Y load model, it means like it's just modeling the Y load. That means like and you can like imagine that like the smaller then the Y is faster, right? The bigger the block, the Y is heavier, is like have a more weight. So because of it, they will model like if the block is 100 cells, so the Y is supposed to be that long. If the load the block is 1K, the Y is longer. The Y means that they model the Y between the cell. Yeah. So let's say they load like for the block of 100 cell, they will model like the Y length, average Y length between like the cell like this. It will be, let's say like a makeup number 10 micron. But if it's a 1K, they will put that like say like 20 micron. And for 10K, they might be like 50 micron, something like that. So this one is better than nothing. However, it's very misleading and it's very incorrect. The reason is that when you have a the like a CF gate, like a random circuit, it's okay. But when you have a very structural circuit, let's say like when you have like this, let's see, can I do? Okay, this one. I just take this one to be. So you have like a pipeline or like a very structured data path. You have this one. It's go like this. Let's say you have a memory to memory, right? It's just get like the data here go to this, go to this and this. This one read out and then put in another one, something like that. So actually it's not real. I just make up here again. But because when you have that, you have this one, let's say like a 32-bit. So 32-bit means that you have design is big, memory is big. However, when it put next to each other, those line is very short. Right? Those are very short because they have to make it short. They have to make it like these two memory. They will be placed next to each other so that like they can connect like very short. Because of it, now even like the cell like this one is a big memory is a big size. It can be like in the 100K, but the length here is very short. So if you model 100K with the previous one, let's say like this, right? 10K, you have 100K, maybe like 100 micron. But in reality, this one is only, let's say like a 10 micron. You have like a 10 times like inaccuracy, right? So the wide load model, it was dead about like 10 or 15 years ago, totally dead. It was dying since 2000 until 2005 or 10, and it completely dead at about 2010. People don't use that anymore. So after that, they use that. That's why they go like they use this one. So they use the real placement and route. So that, let's say like now you have okay, another one is about the placement. So now for the placement, you know that here, right? You know here. This another thing is about the routing. The routing, for example, like for the routing, let's say you have, let me go here, from here to here. It like it have the Y like this, right? And then like, but this part is critical. Let's say like, you know that this one is critical. Because it's critical, so you need to make it faster, right? One of the way to make it much faster, if you remember, you have to make both this one and this one. The cell and the Y make both faster. To make the cell faster, you need to like increase the size of it, right? Make it stronger, like the width of the transistor bigger. To make the Y here faster, you have to have like the width. Again, here's the width. You have to make it larger so that the resistance is smaller, right? So which is, I think, which is what we do usually is we assign that to some like a special rule, which is NDR, non-default rule. The default is the minimum size. Non-default rule will have like a bigger width. Okay, so when in like actually like when we know that in the placement route, during the placement route, that means during the place, and then we go to the routing, we know this one is a critical. Then we will like assign the NDR so that it get thicker, it get wider. Thicker is not. When we say thicker, it means like the wider. Because it gets wider, it means like it speed up this length, this Y delay. But in the synthesis, it didn't know that, right? It didn't know that like, oh, from here to here, I just like the placement give me like I have that. So the distance between the two is like say like D1. But you fit that information back to the synthesis. But you need also to fit the critical net with the NDR to the synthesis so that it knows that, oh, okay, this net is like the NDR. So when I calculate, I go back to the synthesis, right? Synthesis here, I will calculate this portion, right? This one's kind of like a critical. I will calculate that using the NDR rule instead of the regular rule. Because if remember, if you use NDR, then the delay of that net, delay of this one, if you use this one's the NDR, then the delay of that will be different. Because it's different, right? So it's a speed up, then you know that like, oh, okay, you optimize that, and so on. So that's why I think they need the PNR back to the synthesis. That's why I think, that's why I said that like the logic synthesis nowadays, it is tied very closely with the PD. The reason is like because this like Y delay here is like in the critical part, it can be easily in the range of 50 to like 60-70%. So we have to like the logic synthesis need to understand that. The paper I sent to one, I think I sent to one of the student. That one is the algorithm for logic synthesis, and that one is in the old days, which deal with like only like the cell delay, which is they assume that the Y delay is 0. So the purpose or the target of the logic synthesis is to make the total delay of the path, to minimize the total delay of the path. And the total delay of the path means that the total delay of all the cells only. So it will be interpreted as like the first of all, one of the metrics to measure the performance, the performance of the circuit is the delay of the cell at the time, right? For the logic synthesis. So for but the first thing to do in the logic synthesis is you have to reduce the number of the number of the logic stages in the path. You can imagine that like a path normally with the 3 stages will be faster than a path with 10 logic stages, right? I call one logic stage is one cell, right? Regardless if it's like a inverter, buffer, or like NAND or NOR or exclusive OR and so on. At the first optimization for logic synthesis, they will minimize the number of logic gate. Then later they will go to they will assign the weight kind of roughly because they assign the weight of the logic cell. For example, like assign like the unit will be the inverter, and the buffer will be 1.2, and then you have go to the NAND gate, it will be like maybe 1.5, and they have some weight like that. So when they have some weight like that, they will synthesize. So that's the next step of the logic synthesis. The next after that they can because when they do a logic synthesis, there's a two step. One is the factorization, like a minimization of the Boolean network. That one doesn't have any real cell in there. They just try to minimize the number of logic only. Later on, when it go to the step of a mapping, so they have okay. So those in I think I'm going to get sidetracked here. That's fine. So I think the logic synthesis here need the rough PNR, and the rough PNR here is not what I need. And then you know that so those logic design in logic synthesis in the old days only deal with the cell delay. The modern logic design, the modern logic synthesis, has to deal with the PNR information. And not only with that, they have to deal with the power. Okay, I just get that into your mind. Keep that PPAS, right? First of all, get that deal with the performance. After that, power, area, cost. So the next one, I think as I talked about already, is a test, and then you have this one is a design for test, DFT, and then you have a layout design is PD. All right. So this thing is just give you some idea, the scope of where we are, right? So I think we talk about that. The first thing here is this one is kind of all the system or application, right? So we know that system, the semiconductor, the chip is the chips are everywhere. Cannot find I think the future is right now it's not really it's everywhere, but still have something missing, right? But you can see that the effect of the chip shortage in the world right now that affect the car industry, right? The car industry, I think you have maybe not been no, but the car industry in the world right now is in the turmoil, in the trouble because they don't have the chip. Imagine that the chip costs. You know how much the chip costs in the car? Not much. The car costs from $20,000 up to $100,000. However, the chip they implemented in that not much, couple a maximum about couple $100. But because of it, lacking of the chip, the manufacturing the manufacturer cannot have the cost done, or the cost cannot work. The chip is kind of the brand, right? Without that, nowadays, without the chip, the cost cannot work. So I think I talked about that before, but you can see that more and more we see everything will be dependent on the chip. Okay, so This slide talk about the system integration. So here there's a two level of that, when the SoC and SiP. The SoC is a system on chip, right? And another one is a system in package. So I talked about that already just now. I just remind you about what is the difference between the two. So the SoC is like when you have the block are in the same substrate. That's SoC. So because it's the chip, right? It's same chip, which means this one is same substrate. So this one, when it's the same substrate, the connection between them is really the middle. The middle in the connection here is like the internal middle, which is like the mask. You have like a cell connect to the other one is like by the middle, which is implemented by the mask, the regular mask. Here, when it's like in the silicon, like a system in package. This one is when you have the block here, they have a different substrate. Because they have a different substrate, the connection between them will be like by the Y bond, which is like by the, not by the connection between them here, they will have some like kind of special layers to connect between them. Because of it, like the connection between them here, it is not like it's not as effective as this one. However, it has the advantage that you have this, then you can have a different substrate, you can have a different technologies to connect between them. For example, you have here the CPU chip, the memory chip, right? So you can swap like this CPU chip can be at let's say like the 4 nanometer. This memory chip can be a 5 nanometer, and this one can be like a 7 nanometer, for example. Make up again. But for the real work, like when you have the chip with the analog, right? The analog and also with the digital. Analog chips are always behind the digital chip. Currently, the digital chips is at the cutting edge, like a 4, 3 nanometer, as I talked before. But for the analog chips, you know which node they are? They are at the, maybe, let me see. They are at about like a 28 nanometer at best. And then you know from 28 to 4 nanometer, how many nodes between? And 28, 20, 14, 10, 7, 5, 4, 7 generations. The reason that the analog doesn't need to be like at the cutting edge is because analog chips usually like they don't need that. They don't need to be at the cutting edge because they cells like the circuit are usually like a big one, and then they run like at the different like they are in different world. Then they use the capacitance, they use the resistance, those in, because they are in the integrated circuit, so they need to be implemented using the silicon. So those value are big in let's say like the analog work is, for example, like the amplifier for the audio. The audio working, the frequency working is you see that is from like 20 hertz to 20 kilohertz, right? So compare that with what we run in the digital world is a gigahertz. So you compare that to see that like the analog run in the very low frequency, because low frequency, it means that the C and R or L, those things need to be big to like to be like in to be corresponding to the low frequency for the bandwidth, right? So the trend of that, like when they do the SoC or the SiP, the trend is to make like things smaller. So they have a small footprint. Small footprint, you can see that why, right? The thing is, for example, here, I think I need to talk a little bit about this. For the SoC, if you put like those like a CPU, SAC, and memory in the PCB, printed circuit board, the connection between the memory and the CPU on the chip here, the connection between them will be realized, implemented by using the metal in the PCB. The PCB, so you see that in the PCB, the metal, the connection between the chip, right, between the chip like this, is a visual, right? It's like a visible to our eyes, which is it at least like in the range of like usually I think it's about like 210 or 310, about 210 or 310 of millimeter. Is that right? Yeah, about that. But in here, the connection here is the size, the width of the interconnect inside the chip, and it's only 10 nanometer for the 4 nano for the nanometer technology. 10 nanometer here, here's like a 210 of millimeter. You can see how much is different, right? How big a difference can be. Because of it, when you have a big like a, and along with that, the distance between them could be in the centimeter. Here, the difference, like the distance between them would be like a micron. So with that, you can see like when you have like a smaller width and like a shorter length, the consequence would be the capacitance would be lower, right? Capacitance lower and resistance would be too. The consequence of these two would be like power is a CV squared. Which means you see that it's a proportional to the frequency, it's a proportional to C. So lower C, lower power, right? Lower C, lower power here. And then lower C is also high performance because it's also like we are shorter, like the R, the resistance and capacitance are lower. That also means high performance. That's why they try to make like in the when you have a SoC, it will be that way. Okay. There will be one more thing. It's like a miniaturize the chip. It will have something like it's a very critical for two other fields. One is a spine, right? For spine, you will see like in the actually I think you watch the James Bond 007, right? So there's thing like a very fancy thing, but it's not far from the reality because you have seen that like it they can like miniaturize the thing and then they can put anywhere. So this really like a very like a things yeah, I'll be off track a little bit, like off the topic, but you know, all the science fiction movie in the US, I think it's very good because if you watch it and you observe it, a lot of things happen like later on, like within like 10 or 20 years. Whatever happened now, it was like in the fiction movie here. I really admire those people have a very creative, very creative like a mind, so they just predict and they have things like that. Okay, now back. So we have here then that's the spine, the one, and then like another one is like when you miniaturize the chip, it's very critical for the healthcare industry and also for the like a cyborg, right? You know what is a cyborg? Cyborg is the human with the help of the AI of the robotic, and then that's the cyborg. We are currently a certain type of cyborg because imagine that you go right, you go out without your cell phone. So somebody asks you about something, you cannot Google it. Is really you dependent on your cell phone, right, and the internet. So we are in some kind of cyborg right now without knowing that we are a cyborg, but we are very beginning of it because someday, for example, right now, I think at my time, maybe I don't know if your time, we had to learn about like how to take like the square root of like a number. Right now, people don't know it because it's not needed because we have the calculator. Going forward, now with the computer, we have a lot of things that we can do with the computer, and we don't care to do that manually. So currently, we have a lot of things like we rely on computer, or let's say like one thing is we use like the calendar. As I use it a lot. You have a schedule, right? A lot of schedule. How can you handle that? Before you have a notebook, you know that okay, today I meet somebody, tomorrow I have a task to do, and so on. Everything now you put in the calendar, Google Calendar or like iPhone calendar, whatever calendar you need, you have it, right? If you lose it, it means that you are like you lost a part of your schedule, right? You lost your capability of executing those tasks, which means it like hurt your whatever career, your like productivity and so on. So which is you depends on it. Without this, you cannot function normally anymore. So currently, and then now I think going forward, like going forward in the future, the cyborg is like you see like in the mind, I think people's mind, cyborg is kind of with the head, with a lot of sensor, and then like the calculating unit somewhere, and then like it function like a robot. But we are on the way to go that. So how can we do that? That's all the thing. If you have a sensor put on your hand that big, then it's not working, right? But if you have a sensor and the processor is kind of like tiny, you just put and nobody knows, right? The sensor put on your hand and nobody knows, and then you have your processor. It's just like a kind of like a bin, like a pill. You put that like wherever, like in your belt or your like in your pocket and so on. Nobody knows, right? And then with that, then you can become a cyborg. And then like that's the way that like it go forward. I don't know how long will it take, but I believe that like cyborg is what we will become. I don't know how long. So that's like a critical for the system integration here. That's I just talk our topic, but again, those things is like the thing you learn so that like that's why I think I talk about that so you know people are doing what, right? What people are doing, and then like the kind of the state of the art. Now with the system design flow, I think this one is again, I think this one is straightforward. You can read that and understand. I have nothing else to add. Now, requirement for the system design. So this one is similar to what I talked about before. Is like when they have a spec, right? When they want to when like people want to design a chip, they have to specify, right? They have to have a LSI, the spec, or the specific here. They have the spec, but how to get into that spec? And the thing is that they need to have a market to do it, because the market will, first of all, the market will control it. I will talk about like the market will be controlled by designer later, as like a Steve Jobs tried to do it. But first of all, what we want to design is what market want. Customer is the king. So what market wants. So there's the companies, and there's the companies like specialize in researching, in analyzing the market and see that where's the market going, right? For example, like you see the cell phone, right? The cell phone now, the trend now is like if you see like what is it, what differentiate between the iPhone and the Samsung, or like or with the Motorola or whatever, right? What differentiate, or Google? Currently, there's a currently from the hardware perspective, the only thing like this differentiating them is the camera, because that's why I see, and then like that's what like people put a lot of work of like research in that. For example, like you see that like Apple has they okay, first of all, a couple years ago, Google have a very good camera. It can take, it could take the photo, the picture in the dark, because the picture is processed after like taken like into the memory. So they use the software to improve the quality of the picture. So at the time, couple of years ago, at the time, Google was the king of the low light photo thing. But later on, I think after like 1 or 2 years, iPhone see that it's a market trend. So it just like improve, put more money, more research in there, and now it's catching up. Now I think we can see that like there's like the quality of the Apple, the iPhone, and the Google is kind of similar. And then also like Samsung is catching up too. So you see that. And then like they try to differentiate with each other by putting like the quality, like by focusing making the photo quality as the best. Beside that, you have like the speed of the processor. I think we achieve some kind of strength of the CPU at a point that like we don't need much improvement. The same thing with the laptop, right? I'm still using a laptop like 8 years ago, still like very smooth. I don't need anything because I don't play game for sure. If you guys are play game, it's different. But I don't play game. It's just for the productivity, which is just like a softnet doing the Microsoft things and then like doing not much thing. So the laptop is 10 years ago, still working well. To say that this hardware reach a point that is satisfying the need of the market. So what is like controlling like what but for the people like for the gamer it's different story. So you see that most of the things like they spend money on is on the GPU card from like NVIDIA or like from AMD. So come back to like the market trends, right? And the customer needs. That's what I think we talk about. And again, cannot escape the performance, the PPAS. So you see that performance, feature, power dissipation, reliability, price, all kind of thing, but it come down to PPAS. All right, so the next thing, there's a one thing here. This statement is a little bit like confusing. I think it might mean like the demand for time to market is increasing, right? I think the demand for time to market is even stronger. That means like time to market need to be like faster. So in the past, I think for example, Intel used to be like they produce like a new generation every 2 years. Similar to like similar is not the same. Similar to the law, the Moore law, right? You know the Moore law, right? Which is like the technology will be will have a new technology, new node every 18 months. So every 18 months they have a new node. Along with that, Intel will have a new CPU. Nowadays, it's not that. It will be every year. That's for Intel. But it's even more like pressing for the other one, and for like the smaller customer, for a smaller design actually, like for like the DSP, for the memory. Those things is like it come out every 6 months. The design every 6 months they have a new design because of the competition. That's a good for competition, right? I think one thing I'm sure, wherever has a competition, only it can only be good because like the customer will be the one who benefit because they will either they got like a better design, better like better experience or a better like a product, or they get like a cheaper product for sure because they compete. So because of competition, we have time is faster, but put a lot of pressure on the designer, which is us. So the competition in the chip industry is enormous. Is I don't know what to say. It's deadly actually. So then because of it, but when there's one thing. When they put they dump out or like they produce it too fast, you can imagine one thing. The you don't have time we don't have time to think deeply or like to like have a new architecture, right? Let's say if you have 6 months to do something, then during that 6 months you can only do some like kind of patch up, which is you can fix the bug, you can like fix the bug like the feedback from the customer, you can add some feature here and there like a minor feature, so that you can demo out the product, only that. So the patching the bug or like a debug thing and then or like a minor feature can leave us for so long, right? Maybe 1 or 2 years. After 1 or 2 years, all the bugs are fixed. So you need some time to have a new feature like a new architecture. Then it needs at least 1 or 2 years. That's why I think like right now we have a new approach that like we do that both. So they do that both. One is like they have 6 months. We still have to dump out the products every 6 months. However, there's also like the team to work that on the long term, which is 1-2 years to have a new architecture for the new like for the future. So that they can like compete with each other. Complexity is increasing, no question about that. Need for performance is increasing for sure. Everything, right? Fabrication is increasing. I think I show you something like I show you the picture some time back. It's about 500 million for design. That's not everybody can do it. Only the big guy can do it. Early prototype. This one is for the emulator thing. I think we have. Okay, this thing. Let me finish this one. So for the first of all, they have the system, right? After like negotiate and then like gathering the information from the market, from the customer, they have some, and then also based on the current design. So they have a statement. They determine that here is the function need to be done, need to be like implemented. Here's the requirement and so on, right? Then with that, they will like implement that at the system level, which is like you see the functional description algorithm. They see that, they do that, and then like they do that at the C level, and then they will convert that into like a FPGA based prototype. So here, when they do that, I convert it to that. Don't think that is used directly from the C into that. They still have to like do the some kind of like a synthesis, like they have to, and then like but they map into the FPGA instead of mapping into the physical design, like the custom design. So they have to map. It means like you have to convert that into the FPGA, right? So the process is similar to like when you want to do that in the what we are describing right now is like the custom design, which is like every circuit we produce is custom. It's not the same, right? It's totally different from the other. So we call that like it depends on our specific spec. That's why it's called custom. So the thing is with FPGA. FPGA is just a circuit. There's like a bunch of like a cell. FPGA cell in there is called like a LUT cell. Like a LUT, it means a lookup table. So the lookup table basically is like a memory. It has like some kind of get array in there, but programmable by the bit stored in the lookup table. When you, let's say that you want a circuit of like let's say make it like the multiplexer 4 inputs. Then you have multiplexer of 4 inputs. You will specify the code to that LUT something. Then when you specify the code, that LUT block will be converted into a multiplexer. So that's the way like FPGA, right? So and then after that you can like you don't like that anymore. You have another netlist, you have another design. You can reprogram that to have a different like design. That's why they use the FPGA, because FPGA can be programmed to have a different specification. So when they convert that into FPGA, so those things is just like a rough estimate. Then they will run like the software, like the emulator. Emulator means like emulate. Emulate means like you just like imitate, right? Imitate this one. The functional here, you kind of like run the emulator to emulate that, and then at the end you see that, oh, with this, is that the function like how is the function like working? Is that working as expected? And you see that is like actually the high split simulation here. Those things. Let me see. This one is cannot be like they cannot emulate the speed because FPGA is slow. So they cannot like emulate that. They can simulate for the speed. I think it's some kind of like missing here, but they cannot like emulate for the speed, but they emulate to prove that this concept, the function, is working. That's the early prototype. So to be short, early prototype is you take a function description, an algorithm, you try to like synthesize that, convert it into FPGA, and prove that the concept is working. That's the first step. Then we take a break.